fact, the slides are just to make you a little bit worried, but doesn't matter. This study starts from the consideration that there is formations of plasmons at the interface between electrons and electrolytes, or an interface between metals and gas giving low charge. What we want to study is the effect that these plasmons play on the dynamics of charged particles embedded in metal lattice, like Palladium or nickel. This is a reference, as you can see, is the surface of the transformation in metal electrolyte interface electrodynamics. It's well clear that such a phenomenon has been experienced in material with proper surface condition that can affect the formation of plasmons. The model we developed takes advantage of the similarity between lattice region staying around the tetrahedral sites and radiofrequency confining traps for ions. We can consider hydrogen isotopes in lattice as ions because of their electron is mainly in the deep bands of the palladium or nickel atoms due to the Kennell bonds. Let's have a look of the particular structure of the lattice cell. So the yellow spheres are palladium or nickel atoms, the red small one are hydrogen or neutrons and in the tetrahedral site, and the white small sphere are tetrahedral sites. We can see that the tetrahedral sites belong to the intersection of these two planes, the 101 plane and the 101 bar plane. Then, if oscillation of electrons at Fermi level of the metal atoms takes place, we have the creation of electromagnetic field in this region. So we know that electrons are allowed to move to the tetrahedral site when the loading is close to 1, just to avoid that their chemical potential diverges. Here is a schematic representation of the Palladium lattice cell. As you can see, this region around the tetrahedral sides is showing a cylindrical symmetry, and this can help us in modeling the system. In order to have a simplified picture of the apparatus, we can make a projection of such a schematic view in the plane of the slides, obtaining the 101 plane staying along this line, and 101 bar plane staying along this other line. And black spheres are palladium atoms. As you can see, when we have oscillation of the electron flows at Fermi level, we have charge separation that creates such electric field along the plane. So it's a negative charge here, positive charge here. That means that if we know exactly what is the frequencies of the oscillating electrons, we can obtain time-varying forces with an intensity which is proportional to the distance from the central region of the system. Let's go on with the mathematical model. It takes into account just the balance of force, giving us the equation of motion. Here we have the repulsive current force times the Thomas Fermi screening factor, and here we have the force of the trap acting on the ions. It's with some previous mathematical arrangement, we can make in explicit form the force for the Coulomb effect. This is Q1 and Q2 are the charge of the particles, R1 and R2 are the radial coordinates of the particles, K1 is just a unit vector pointing from particle 1 to particle 2 or vice versa, and that's all. So, here we have the expression of the trapped force that are obtained considering that the oscillating system can be well described as an oscillating dipole, but other expressions have been experienced to try to monitor this effect, like circular symmetric potential, with giving the same results, more or less. Here we have alpha, which is a factor ranging between 0 and 1, modifying the peak value of the signal because of the orientation of the oscillation with respect to a plane. L0 is the radius of the trap, and gamma is a form factor close to 1 that avoid the singularity effect at trap edge. Here K is the electron charge, and time is the number of electrons which participate in the oscillation for each atom. From the literature, we can know how many electrons we have for atom. We can assume that the number of electrons participating in such oscillation are equal to the density of the state at Fermi level. Then we have about 10 electrons for nickel and 6 electrons for palladium. That means that in the nickel the signal can be larger than in palladium. And also the frequency is a function of the electron density, as you can see here. So in nickel and in palladium there is a small difference in the electron frequency. The signal that the potential, the shape of the potential inside the confining region is like this. So we have the trap potential at two different times, is oscillating, plus this delta Dirac like at middle, that is due to the presence of the other charged particles. Well, at the end, the explicit form, the explicit dimensionless expression of the equation of the motive is this one. Well, it's important to observe that such equations are modifying equations. Having an attractor-like behavior if their coefficients are in a narrow region. So otherwise, the system becomes really chaotic. For people interested in this topic, I can suggest this lecture from Nature or some other from Physical WP. You can see here the region of the parameter allowing to have a good solution of the problem. And I don't know if it is just occasional that we have stability in our system at this so small scale. Let me show the results. As I have shown before, the equations are highly nonlinear, so the solution depends on the initial condition. It's strongly affected by the initial condition. So if we have a pattern staying in the tetrahedral side, and another one arriving from the outside at thermal energy because of the diffusive process, we can see that with proper bound initial condition, we have a strong approaching up to 10 to the minus 2 angstrom, and the particles gain about 3 keV of energy from the trap. The same calculation has been done in the nickel just to see what's happening in case of studying the interaction of a deuteron with nickel atom in the lattice. We can see that also in this case the distance decreased up to 0.1 angstrom, and the particle here, because of the higher value of the nickel signal, increases above 4 keV. Last case is interaction of alpha particle that is supposed to be created in the system with the nickel atom. We can see the same behavior because even if the repulsive effect is larger in this case, the effect of the trap force on the charged particles is also higher because of the particles is carrying 2 charge instead of 1. And its energy increases above 8 keV. So we can extrapolate such information just to see, just to consider that for higher charged particles, we can have enough energy to produce itself. When the boundary conditions are not good enough, we don't have collision at all, like in this case. I have also done quantum mechanical calculation for the case particles having low energy when they are very close. So when the wavelength of the emitting particles is in the order of the distance with target one. So the results are the following. This is the shape of the potential here. And this is the evolution, considering that the particles can be treated as a wave packet moving in the lattice. So you can see that the evolution of the wave function of the square module of the wave function. So you see that a fraction of the wave is reflected and the other one is transmitted. I think that we can make conclusion that the model showed that the signal produced by the charge density oscillation around the metal atoms produce interesting trajectories of the deuterons within metal lattice. And the combined effect of the trap force and non-linearity produce a collision effect. During their dynamics, the particles approach one to the other at a distance that is very, very well below their average value in lattice. Well, we cannot exclude it in principle, so interaction between protons from between deuterons and between deuterons, protons, and host metal atoms. And we have to consider also that the electromagnetic field is very strong, so the electric field is in the order of 10 to the 15, 10 to the 14 volts per meter. So we can modify the reaction chart. These last slides, and this is a bridge. This seems the bridge of McKubre, and it reminds me that we are creating a bridge between all the area of scientific knowledge, and that means that for a better understanding of our problem, we have to take in contact all the knowledge topics of the science.
Before we get to any questions, I'll just ask everyone to hang on after the questions. There's just a few announcements to make. So any questions? Anyone at all?
Have you thought at all how one lattice, the dynamics of protons in the system must be extremely strange. Basically, I mean, globally, they behave as though they are unbound. So locally, there must be some extremely strange dynamics. And have you thought whether one could get some information from the bipolar factors or the bipolar factors from neutron scattering or the dynamics of neutron scattering about the dynamics of those particles in the lattice?
No, thank you.
I gather this is all on a surface bed. Could it be a surface of a grain boundary deep down in the bowels of the metal? Or does it have to be right at, say, the obvious surface, or am I misinterpreting your
Well, this is a good question, Tom. I forgot to highlight that the people studying such a phenomenon have discovered that the enhancement is observed at a distance up to hundreds of angstrom from the surface. So there is about a fraction of a micron involved in it, but maybe more.
above the surface?
Below the surface.
Below the surface?
Yes, to the above.
I think I missed it. This was nickel? Was this nickel or was this palladium?
Well, it's the same, because the cell shows the same shape. So we have a center base cubic system.
Okay, so I guess that answers my second question. You weren't including any magnetic effects then?
Well, I evaluated the contribution of the magnetic field into the currents of the
Yes,
vibrations in lattice. That is about 7 order of magnitude less of the.
It's just that the density
in terms of energy, so the graphs show a very high value of energy to field. I mean, it's in the order of 45 or more photons. The contribution of the magnetic components is a bit low.
Well, it's just that the density stays at the Fermi level for the nickel has a splitting in it. You have, there's a magnetic moment, and so part of it is reduced.
Well, I didn't consider it.
I mean, I don't remember exactly what it is, but it's got a small moment of about 0.7. So it's an imbalance.
Okay, thank you, Dr. Violante. That wraps up our session this afternoon. If you check your watches, you'll notice that we've come in pretty much on time. I had lunch with Dave Nagel, who coached me extensively on how to bring a scientific session in on time. And I'd like to thank my colleague, Dr. Oriani, as well. I'd like to remind everyone that this evening in Ballroom A is the workshop, the low-level nuclear workshop with Professors Takahashi and Kennell. And they'll be in Ballroom A this evening starting at 7:30. Also, for tomorrow morning, you'll notice if you check your blue insert, which was put into your book of abstracts, that breakfast tomorrow morning starts at 8:30 and not at 7 o'clock. And I think if the organizers had put a little more thought into this after last night, I think we could have used the extra sleep in this morning. Some of us, anyway. The other thing to note about breakfast tomorrow morning is that it's not in meeting rooms, the meeting room that it has been in, but it's in the harbor view room. And then that goes from 8:30 to 9:30, and then we'll see everyone at 9:30 for the scientific summary from Dr. Bersani and McKubre, and a question and answer.
Applaud everyone for having the stamina to come to a session at 7:30 on the 4th day of the conference, and so we'll hopefully be able to make your perseverance pay off. And one of the definitions of an expert is someone who has made lots of mistakes. And so on that basis, I think we can all be very thankful to was created, and he found somebody as big expert as me to help put this workshop together. Also, I'd like to introduce my colleague and friend, Professor Takahashi from Osaka University. And the way that we've structured the workshop is that Dr. Takahashi will explain the principles of radiation detection and how to do radiation detection correctly. And then I, being the expert, will explain how to do it incorrectly and give some examples of measurements that were made that appear to be good but actually are not good. We don't think that we can teach, although Professor Takahashi is well known as a very gifted instructor, it's probably not possible to teach good technique in a 1 hour session, but I think what we can do is to kind of elevate everyone's consciousness of the difficulties involved in radiation detection and also some of the ways that these difficulties can be overcome so that we can help you to be critics not only of yourselves but of other people's claims and experiments as they're presented in this or at other conferences. And with that, without further ado, I'd like to turn the session over to Professor Takahashi.
I have prepared a lot of material on security. So in Osaka, so can have plenty of time. So we talk about the neutron detection, X-ray detection, and charge detection. These three will be the most three important techniques related to code-driven experiments. However, today, I think it's better to concentrate just on this charge particle detection and especially spectroscopy technique, because this is the most matching to this conference. And if we have free time, I will be able to touch on X-ray and neutron. Probably. Before starting, I'd like to say to make any kind of radiation detection in contribution work, we have to notice firstly, if with the assumption we try to use the Palladium deuteride in steady condition, probably we will not be able to detect anything, even by using the most elegant and the most sensitive and the most expensive detector, like Kamiokande, because the detector range of the phenomenon would be far beyond the stable. That is very necessary. And after such simulation or so, maybe we can use the conventional technique with careful techniques. So let me concentrate on the swing to charge particle measurement. I'm sorry, sounds a little in Japanese. I can have a contrast. This is a typical beam irradiation experiment to measure charge particle coming out from some metal deuteride sample and using a sort of, say, low energy deuteron beam in this case. And the typical method is the project a sample on some cooling device to control the temperature of the sample and irradiate the beam from top side and changing the beam energy and current also. And we try to observe the emitted charge particle typically by using a silicon surface barrier detector with diffusion thickness mostly 200 micrometer in most cases. In some cases, we use a thick silicon surface barrier detector, say 3 millimeter diameter. That depends on the purpose of the experiment. And usually, we will set up the aluminum screen point in front of silicon detector to eliminate all the scattered neutron or beam by a sample coming this way. And in this case, we set up about 3 micrometer aluminum. That is enough to stop all the scattered neutron coming into silicon surface barrier detector. If we don't use this, we have too much signal coming in, and we have a radiation damage problem to silicon surface barrier detector. And also, we surround the detector with some metal cylindrical shield for electromagnetic radiation. That is also necessary to take the noise signal or eliminate noise signal. Probably Dr. Kennell will touch on this later. And just a very standard. And by using this kind of setting up, we can make in principle, but to do more, to take more information, we do more by setting up other detectors for measuring X-ray, for example, by a beryllium window here, it's a 100 micrometer thickness. So this side of vacuum, so the X-ray detector, in this case again silicon SSD, this is special for detecting low energy X-rays, say less than 20 keV to 1 keV we can detect through this beryllium window. And the other is, this is for charge particle measurement, silicon SSD, and others for detecting gamma ray, the outside vacuum, and also we have a neutron detector, Ne213 for neutron spectroscopy. And by using this kind of 4 detectors for charge particle, X-ray, gamma ray, and neutron, we can make somewhat combinational measurement and to make a cross-checking between different type of radiations. And then we irradiate the beam by changing the beam energy, in this case from 10 to 300 keV per atom, per ion, and changing the beam current, in this case up to 400 microampere, to observe the elliptic pattern. And this kind of experiment, I didn't show this time, but my Chinese colleague from Institute of Modern Physics, Lanzhou, have made some interesting work in my laboratory, and wanted to come here to present the paper. He could not come for financial problems, so I very shortly touch on this. This is a typical proton and triton peak by DD reaction from Palladium sample in this case. Sorry for the Japanese written here. And this is the typical noise coming this way. So to detect the tritium very clearly, we have some caution. We need some caution. And this is an experiment changing the beam energy and also using a molecular ion beam. This D3, just a triatomic molecule. We are doing the experiment by changing beam energy per deuteron and irradiating sample alternatively by single monoatomic beam and then molecular ion beam, D3, by setting the energy per deuteron just the same and alternatively, and taking a ratio for DD reaction production rate, and we got this kind of results. So this is already something to do with, we have some kind of blood-body interaction for DD reaction by comparing single atomic and molecular ion beam. We will have a three-body full interaction effect, I think, here. And this kind of effect also appears in the X-ray emission rate. If we compare the X-ray emission rate as a function of beam energy per atom, we'll see the difference between atomic ion and molecular ion. I think this is a kind of interesting and very basic experiment. Probably we need to study this kind of problem from now on. And also, this is the X-ray spectrum. However, we have to take caution about the X-ray spectrum because usually the characteristic X-ray we have up to 100, this is 260 kV, about 100 kV. That's uranium characteristic X-ray. Over there, it should be some kind of Compton gamma ray coming in. So this is a very common knowledge. And compared with this gamma ray spectrum, this is a foreground, this is a background, this is a natural background. This is a calcium and so on. And this extent of very high energy. And we saw up to 26, 24 million electron volt. We have such kind of gamma ray. I don't touch on the detail of this system because I don't have much time. And this is very typical and well-known result of charge particle emission. But sometimes when we irradiate the shift Palladium sample here with very intense beam current, like 400 microampere with 40 keV deuterium energy, we see proton and triton is okay, but we see just some kind of anomalous peak, very spread. What is this is the problem? So we need to check, for example, the waveform of the pulse. This is a typical waveform coming from silicon SSD. This is a proton signal. This is a high energy signal coming in. And we have some other kind of signal. This is a piled up signal. And other signal is a very broad one. This would be noise from somewhere by mechanical vibration, for example. And in addition, we have another kind of noise signal. If you see this is a signal out from preamplifier. This is a normal signal. This is electromagnetic noise, linking signal, typical. If we count this kind of things by multi-channel scaling, for example, we have burst-like events usually detected. This is very makes artifact. Anyway, by taking a caution about this kind of problem and checking the signal, we can say, well, this is the ideal signal. And this is another example of the measure results by using 1 millimeter thick titanium plate, but without preloading the deuterium, and measure the charge particle spectrum coming out as a function of energy. And we saw here the high energy signal. This is somewhat similar to the spectra measured by Professor Kasagi, Tokyo University. Is maybe proton or deuteron, and extended up to 16 MeV or so. This is a double pyrap. Something meaningful later we found, but we have a pyrap spectrum like this, but at that stage we didn't notice about this. And it's maybe private. How is rounded so far. So to identify this kind of anomalous signal, we need to identify particle types and, if possible, the peak energy spectrum. If we have a characteristic peak in energy spectrum, and if we can identify the type of particle, then we can mostly identify the type of reaction. So for that purpose, the well-known technique, counter telescope by delta EE spectrometer, the numerical analysis And however, in combination with one-dimensional analysis, that is necessary in this kind of measurement because we have to measure the wide range of charge spectrum from low energy to high energy. So we need a little bit modification from conventional technique. This is typical experimental condition for using the low energy deuterium beam implantation. And this is a case I already presented on Monday by using a highly pre-loaded titanium sample. But it's not essence. Essence is the methodology for counter telescope by using delta E. Delta E detector in this case we use a rather thick detector. I'll mention the reason very soon. And then E detector, 150 micrometer of depletion layer of silicon surface barrier detector. And in addition, it's better to use a full energy detector, which we call here the EK detector. K means the kinetic energy of particle. So we need to detect directly emitted kinetic energy in full scale. And in this spectrometer, the energy is shared into delta E in E detector. So we have to recompute radar. And so combining these two-dimensional information and one-dimensional full energy spectrum information and also one-dimensional energy loss spectrum and E spectrum, and by combining these four information, four data, we can make somewhat complex, but I think very convinced analysis about the charge particle identification and spectroscopy. So this is a real example. Beam coming in, we set up a detector in this way. This is the EK detector, this is a delta E detector covered with screen wire and electromagnetic shield, and we take a signal in this way. By a amplifier, we take the energy spectrum for E detector, and delta E detector, and total energy detector, EK detector, and also from here we are taking a window for proton peak, 3 MeV proton, and registering the time variation of count rate. This shows the yield of DD reaction, usually two-body DD reaction. This is a reference of the reaction. And then the most important one is this two-dimensional delta E two-dimensional spectrum with coincidence. And to select the detector thickness and times, probably that depends on the purpose of the measurement. In this case, we wanted to detect the, so to say, three-body fusion product, like triton and helium-3, about 4.8 MeV. So we estimate the energy loss by screening oil and delta E detector. If we use the rather thick detector, the helium-3 detector will fully absorbed by delta E detector. However, we can have a somewhat separable difference of energy loss between proton and triton. So by using Shinka detector, we can identify a separate proton and triton. If we use a Shina one, this particle will penetrate and get in here, so we can take a coincidence signal for alpha or helium particle. However, we will lose probably information about the separation between proton and triton because of less resolution. So we need to make a somewhat compromise or to use two kinds of delta detector to make a complete experiment. Anyway, we take this kind of two-dimensional spectrum, E and delta E. This is a proton, 3 MeV proton peak, and we have this kind of, in usual case, so-called variation in two-dimensional spectrum. So we have to make a pressure data for energy scale. And this is a typical delta E energy loss spectrum for various particles. This is for 3 MeV proton or 3 MeV triton from DD reaction. And so we can hardly separate, hardly separate, but separate. And if you use a single delta spectrum, just superposed and make a single peak, so we can't separate. And this is a superposition of double pileup of these two proton and proton-triton pileup and triton-triton pileup and so on. And make this kind of shoulder here. At high energy, in principle, we don't have signal for DD reaction, but we sometimes observe this kind of thing. In this case, this is we are identified as alpha particle, and to identify this, we have to calculate the energy resolution of this detector to alpha particle. That we have done by using California, MH241. I want to calculate the time is running, and also to check the this kind of peak is really stopped by delta E detector or penetrates through. That can be checked by comparing this single mode spectrum with a coincidence spectrum from two-dimensional E delta E key. This is a somewhat integrated spectrum over E axis and making a delta E spectrum in coincidence spectrum. And by comparing these two, we can say this part did not reach at the E detector. So this signal stops at the delta E detector. So this may be our signal. And if we see the E spectrum, it's a single mode spectrum. We see this is the proton signal. Triton disappears because triton lost most energy by delta E detector and went this way down. And then we have a double pileup signal like this usually when the count rate is high. However, sometimes we see this kind of strange shoulder. And just we identified in this case as triton, in this case 3.8 MeV. This is we have just coincidence with estimated energies in design. However, we have to be careful about the pileup signal distribution function like this. This is another experiment by using the same Palladium titanium coil and measuring spectrum in this way. It's a proton, it's a double pileup, triple pileup. So the usually pileup signal is this kind of signal, just double here and having a tail this way. This shape is changing by the shaping of amplifier, linear amplifier, and so on. And then we compare the decomposed spectrum from E delta E coincidence and taking out already the proton signal. And so here we should have just a tail of proton, but here we should have only alpha particle and the triton and so on, or deuterium. And from this we did identify this triton as the helium, maybe helium-3, and in full energy detector we have a similar component, but this detects the helium-3 also. This did not detect helium-3 because this was absorbed all by delta E detector. So we understand this is the superposition of two components. But it is not very so clear only with this experiment. And if you see our second experiment, to irradiate the same position after 3 weeks or so, and we change the EK detector to Shinawa in this case. But we are surprised to see this part was separated into two parts by some reason. And we speculate later something like that. Reaction place would be changing from shallower place to deeper place by some reason, maybe by the damage of this area by beam. And so the energy is changing lower side, and this peak didn't change much because this is identified as triton, so it didn't change, lose much energy. So we have a gap in this way. This is a pileup curve. particle. We have two kinds of pileup, proton-proton pileup and triton-proton pileup. This way, anyway. We have to be very cautious on that. And also, here we may have a contamination effect by preacher target. If we have a DT reaction, we have our 3.5 MeV alpha particle, that may appear around here. But in this experiment, when we change the beam energy from 150 to 300 keV, this part increased about 20 times. If it were a DT reaction, this must be decreased. So the result reversed. And also, if we have a secondary reaction by produce triton by DT reaction, that makes a DT reaction also. And also coming around here. If so, the ratio between this one must be constant. So far, these are not such kind of triton contamination functions. And also, we can say the elastic scattering neutron will make a secondary reaction also. In that case, also this ratio, this one and this shoulder must be constant. So far, these are not such contamination. Anyway, we need such kind of analysis of many impurities and so on. And also, we make this kind of delta E spectrum and analysis and comparing the two and normalizing with this peak. This kind of normalization is also necessary because of the difference in viewing solid angle detector and so on. And if we normalize, so we can compare this component with this component. And we see in this way, and almost the same count if we integrate over this area. So we are somewhat confident of the results. These are coming from same reaction channel. However, you have to be careful about this peak. In this case, this proton energy loss peak is somewhat very increased because of the contamination of this typical periodical noise. This is electromagnetic noise, typical. 300 Hz, that means 5 times of 60 Hz. This is a so-called harm. It's coming very easy. So we have to, and also, this is very important to make this kind of, so dimensional or three-dimensional analysis to draw the, so to say, contour map of signal. This is full energy. We already converted from E to E plus delta E. So the particle energy, this is the energy loss. And here we can say we have a alpha peak around here. And this is a pileup signal. Just that we identify a triton signal. Therefore, the energy loss is smaller than proton pileup and larger than proton pileup. Proton is already cut here. So far, this would be the tail of saturated proton signal or neutron. We didn't identify yet. Anyway, we can identify this one and this one from this kind of diagram. And also, if we want to know more, we can make a sliced cut along this axis in this way to see the change of spectrum parasite distribution. For example, at the double pileup peak, that draws this kind of pileup curve. We can use later this kind of pileup function. And the triton window, we have this kind of distribution. That means the triton distribution will be something like this. That is contaminated in this part. So we make a very careful analysis for this. Anyway, by doing this kind of analysis, we can make sophisticated spectroscopy for charged particles to identify particle types and those characteristic energies, and then identify reaction type. Thank you. I'm sorry. I spent too much time.
This may be kind of a unique talk for several reasons. First, I think I'm one of the few people in this conference, either pro or con, that admit to having made Secondly, I've been asked to talk about them. So I feel very privileged in that regard. I also want to emphasize that some of the things I'm going to be talking about are based on my own experiences, and I do not mean to imply that because I'm showing an erroneous result, that means that everybody else's results are erroneous. That's not what I mean to imply at all, but I do hope that I can share with you some of the difficulties that are involved in the field of low-level radiation detection. And indeed, I feel that the talk this evening is really not about cold fusion per se. Rather, I would like to shift my attention to the science of low-level radiation detection in general for whatever purpose, and to note that regardless of what your opinion may be about cold fusion, there will certainly be discoveries in the future in nuclear physics that will depend upon your ability to make good measurements of low-level radiation. So I feel that this is a very valid exercise, regardless of whether we're talking about a cold fusion experiment or some other one. The concerns of cold fusion are really the same as for any other experiment. You have to know, have you got the real thing or not, and what do you do to avoid having a false positive event? How do you recognize that? So there's several different types of errors that can be made. First of all, there are errors that can be made due to the mechanism of the detector itself. I'm going to talk mainly about electromagnetic radiation detectors, but really all radiation detectors are fairly similar, and they all have they're susceptible to certain kinds of errors. There's also some possibility of making errors due to the mathematics of counting and error propagation. What do you do if you add counts that have different run times, how you weight those, and that type of thing? For that, I mainly refer you to a reference such as Radiation Detection and Measurement by Glenn Knoll, but there's also some particular intricacies which I'll point out a little bit later on. There are also possibilities of making errors due to assumptions about background radiation, so that if we get something that's statistically significant, it may still not be due to something in the experiment, but it may be due to something that's unusual about the background radiation that you're comparing it against to. One of the most serious problems, I guess I'd call this one out especially, that I think that the majority of errors that are made in low-level radiation detection measurement have to do with coupling small signals to the counter, because what you're really measuring is not particles, but you're seeing the particles translated to electromagnetic pulses that are being carried along coaxial cables. And if you get pulses from some other source, those can be registered exactly the same as counts, and that can create some significant troubles. There's also a possibility that somebody might invent some totally original kind of error, and I don't wish to discourage creativity during this workshop, but I think really that's probably not as serious a problem as some of the other ones. For detectors which are detecting electromagnetic radiation, there are some types of artifacts that can arise. Let me move this up a little bit. First of all, due to Compton scattering, there are going to be, the detector typically does not simply measure the particle or the quanta at the energy that it exists at. It's very unfortunate, but most detectors measure the particle, maybe at the peak energy, but also at some other energy. By Compton scattering, gamma quanta produce additional counts at lower energies. It's also possible to obtain single or double escape peaks. These are caused by pair production inside the detector where maybe the energy leaves the detector, and that gives a false peak at an energy which could be the actual energy minus 511 for one particle, or minus 1.02 for the pair. See, there are other ways that energy can be lost. That you could lose energy from a K-alpha X-ray escape, in which case the energy will be decreased by the K-alpha X-ray of whatever atom that interacts inside the detector. Also, if you have a really big signal, it's possible that you can get coincidence peaks at the sum of the photon energies that, if they're seen together. And all these kinds of things are things that can be seen by a perfectly functional detector, most of them with, if you have a lot of counts. And so these, those of us who are aspiring to observe cold fusion signals, we would be very pleased indeed if that were the case. If we had too many counts, or if our, and if we did have a perfectly functional detector, it would probably be the first time. Background radiation is a serious problem. We like to think that the background radiation is going to be precisely constant for all time, and that it's always the same. But in fact, that's not true. There can be significant fluctuations due to products of radon and other gaseous isotopes that might be floating around your laboratory. And so that the peaks due to radon depend upon how the experiment is vetted and what possible things, surfaces exist for radon to be absorbed onto. And so, that can change from hour to hour or day to day. Also, there's the possibility of changing the cosmic background, especially if there's something like a solar flare at a particular time. And in some laboratories, the background may vary between day and night, may change even hour to hour. Also, I point out specifically that annihilation radiation is due to several different possible sources, because it's one of the favorite energies that things like to decay at. And so this is often variable in background spectra. It's a good idea to increase your signal-to-noise ratio by using appropriate shielding for just about any detector. That's almost universally true. But in that case, we have to be very careful that the experiment isn't altered in some way as if the shielding is changed, or if the geometry of the experiment changes. That's something that must be taken into account. I also wanted to mention briefly that there is, in addition to just simply making a mathematical mistake using statistics, it's also possible to obtain a false positive peak, especially a 1 value, simply by rejecting data selectively. And that's something that I don't think that we necessarily do consciously or dishonestly, but consider that just about any experiment that you do, well, any experiment that I do, there's usually something wrong with it. Okay, I didn't quite get this thing moved at the right time, or this didn't happen in the right way. And so it's easy to make a measurement and then say, well, I really goofed that up, so I'm going to throw that one away. And especially if you have the benefit, if you have a good spectrum, you keep that one and then throw away the bad one. And if you continue to do that, you can wind up with a peak sort of by accident. What does a peak look like on a gamma ray detector? This is a fairly good, I should say it's a wonderful gamma ray detector, because the guy who lent it to me is in the audience. This came courtesy of Naval Research Laboratory, and this is for a lead-shielded experiment. And so you see that there are several characteristic peaks that are due to background radionuclides, some that are due to the lead itself, as well as radon and atomic testing that was done years ago, and so forth and so on. Also, I'll point out that this particular experiment, I should have probably used some X-ray shielding, but didn't, so that there is a very prominent lead K-alpha X-ray at 75 kilovolts. And if you kind of visualize that, I'm going to come back to that in a little bit. Okay, let me talk about electromagnetic coupling or electromagnetic artifacts. And this, I think, is probably the #1 problem in low-level radiation detection. One way that this can occur is, believe it or not, if you just have mismatched impedances in a cable. Maybe you have a cable that was bought at Walmart or something, and it's not quite the impedance that it's supposed to be, that it can actually reflect pulses and create additional counts. Also, if you have irregularities in a line voltage, you can have electromagnetic artifacts. That can occur, for example, well, a very real problem was that at NHE laboratory, we had all these very delicate experiments that we wanted to run, and meanwhile, Kunomatsu-san downstairs at Inner Japan is running his experiments, and it's probably his fault because he's consuming all kinds of electric power, and therefore he's disturbing the line voltage, and so we're getting bad signals because of things that we have no control over. It may not be so bad, in your laboratory, depending on the stability of the power, but it can be a very serious problem. Also, okay, you can have interference from other different devices that run in your laboratory, and I think, especially these days, computers are notorious because they're running at higher than megahertz, and they're producing signals which can be coupled into the counting circuits of the detectors. At these kinds of frequencies, in other words, at megahertz and above, the concept of electrical ground doesn't really exist. We normally think that, well, if you've got some piece of metal and you've got a wire connecting it to the ground of the laboratory, that must be ground. But that's not true for high frequencies. The complex impedance is what determines true ground, and everything has some AC impedance, and so that you have to be concerned about accidentally making circuits in your counting system, and these can result in different, it can act as an antenna, in other words, a broadcast antenna, and you can wind up making additional counts by mistake. Also, if your experiment is electromagnetically active, particularly difficult, I think, is a plasma experiment. This broadcasts high-frequency radiation, which can be received by the detector and produce a false signal. Let me give an example of some errors. What normally happens, if you have an impedance mismatch in your counting system, what normally happens is that you have low energy noise, and that results in excess counts at low energy. It can be a lot broader, more broadband than this. In fact, I think this actually had some help from a plasma experiment that I was running at the time. But anyway, the peak is always at low energy, but it can be fairly broadband. And there can also be some mini peaks. This is statistically significant. But this could be due to plasma oscillation and particular frequency, which couples into the counting circuits to create a false peak. And this is something, this is not rare, that everybody who aspires to do radiation counting will achieve positive results. The question is whether you believe your positive results or not. So that, I'll say that you need to recognize ringing oscillations in your system, because they will exist even in very, very fine systems. And if you can't get this, just hire a graduate student and you can get it for sure. Now, that's what the characteristic signature is of broadband electromagnetic noise or electromagnetic oscillations. But if you're really clever about it, you can make noise that looks like real signal. And this is something that I made using a plasma experiment, and it looks, for all the world, like a peak from a sodium iodide detector. It's nice and broad, and I even have a Compton plateau here, and not very, I have some counts at high energy, but not very many. So it looks like, looks like the characteristic energy of a peak as seen by a sodium iodide detector, and it even looks like it's got some Compton background in front of it, so that the signal can mimic sodium iodide detector. And this is one of my masterpieces. This requires quite a bit of skill to screw up this badly, but this was done with also with a plasma experiment. And man, this looks like a real high purity germanium detector peak. If you compare that to the real peak at 511, it looks like this thing is, kind of about the same width, and it has sort of the right shape. And in fact, when I first did this, I was sure that it was real. I went back and rechecked the width. It's the wrong width. And also I found out that I could reproduce it. It was fully reproducible, which was an advantage. But also, because it was reproducible, it did yield eventually to the scientific method, and I was able to figure out what was making it. I should also mention that Peter Hagelstein and I collaborated on a peak which was even more remarkable, because we were looking for, at that time, for tungsten K-alpha peaks, which are a doublet, I believe. And we produced a phantom much like this, and it had a doublet structure. And it was only off by 3 keV from where we were looking for. So that was also pretty amazing. But, so I guess the point of putting this up is to sort of put the fear of God into people, that just because you have a signal that looks right doesn't mean that it is right. There are ways to make very good-looking false signals. Also, if your experiment is non-reproducible, it's very difficult to tell what you've got in there. It doesn't mean, if your experiment is non-reproducible, it doesn't mean that you're a pathological scientist. I mean, you may be, but not because of this. But it does mean that the scientific method cannot be used to analyze the experiment. So to really be able to tell whether you've got something real or not, you need to have at least statistical reproducibility. I mean, you don't have to have 100% reproducibility, but maybe you need something like 10, so at least that you can run a series of experiments and obtain the result that you need. Okay, this is really just kind of editorializing, which I'll skip for the moment. Well, maybe I'll give some philosophy here, is that on the other side of that coin is that you don't, in order to have a good experiment, you don't necessarily have to have a satisfactory explanation, because I think all science is empirical. And there are some examples I wanted to cite were like lightning, that people knew about lightning for millions of years, and they didn't know what it was, but they all believed that it existed. And similarly, it wasn't until within, I think, the past 10 years that people understood that bees could fly, or how they flew. But nobody ever doubted that they did fly. It was just that they didn't understand how it happened. So, this is an empirical world, but reproducibility is a problem. Okay, so what do you do? Let me try to give some practical advice as to what you can do if you have a result that looks like a positive result. How do you know if you've got the real thing or not? Well, the first test is to just look at it and decide, does it look right? Does it, if you measure the full width half maximum of the peak, is it the right value for the detector that you have. If it's not, that doesn't prove that it's wrong. I mean, you might have maybe two peaks that are close together that makes, might look like an overly broad peak, but that at least is a clue. If your peak is too skinny, that's bad because you can't make that by accident. But okay, also it doesn't have the right shape. Sometimes the peaks may look good, but actually the shape isn't quite Gaussian, and you can be able to tell it that way. Also, you can use a foil test. And I had, when I made this view graph, I had in mind electromagnetic emission or quanta, but you could also do the same thing for particles. But anyway, if you have something that appears to be emitting gamma rays, let us say, what you can do is to try to attenuate that signal by putting lead in front of it, say. And that should attenuate the signal, and you should be able to calculate about how much attenuation should be expected based upon how thick a shield is that you've made. Then, on the other hand, it's possible that if it's an electromagnetic artifact, that can also be attenuated by metal simply because electromagnetic waves interact with metal. So you can do the same thing with a light metal foil like aluminum foil. And in that case, a gamma ray should go through basically unattenuated by aluminum foil, but an electromagnetic artifact would probably be affected by aluminum foil if it's also affected by lead. Also, let me back up a little bit. That one of the problems that we generically have with cold fusion research is that research funds are very hard to come by. And I know that a lot of people have difficulty in getting the very best detectors, and not everybody can have a high purity germanium detector. One of the scientists here was complaining that he had to sell his wife to the gypsies in order to get a detector for his experiment. And so that some of us may have to use sodium iodide detectors or something that's not as good as germanium detectors. But I think those can still be used and can still give valid information, but you have to interrogate that detector fairly well. One thing that you can do with a scintillation detector is to vary the voltage, or whoops, wait a minute, I'm down here. If you vary the scintillator voltage, that should move the peak left or right. Also, if you vary the gain of the amplifier or preamplifier, that will also change the peak energy. That will happen for a real peak. If it's an electromagnetic artifact, it probably won't affect it, or might do something else. You can also just shut off parts of the system. It's really bad if you take out the power supply and you've still got signal, and that's your first hint that probably it's not real. But these are things that you can do no matter what kind of detector you have, and to try to extract some better information. Oh yeah, let me put this view graph up. It's a little bit out of order. I wanted to mention some other kind of funny errors that I made. One thing I found was that I had an experiment that was done with gas loading, and there was a turbo pump on it, and when I shut off the turbo pump, it would hit a resonance as it decelerates, and that would, for some reason, generate counts, and it looked like I was getting x-rays, but it was really due to the fact that I had shut off this turbo pump. Then the same thing I noticed, after I got tuned into this situation, after I understood this situation, I started trying other kinds of vibrations, and I found out I could make broadband counts with other vibrations. I think a lot of people can talk about stories along this line where if you're working in a large laboratory and the guy next door has this big radiation source and he brings it out once a day to do his experiment, you might see that in your experiment. And if you don't know what he's doing, that can cause you to think that you have bursts of radiation. Also, we found that water condensation on SSB detectors caused extra counts. that's, I guess, we can thank Steve Karchbaker for that observation at SRI. Okay, let me summarize with some recommendations. First is that I think that it's a good idea to use more than one technique whenever possible for measuring radiation. And in addition to, the preferred technique is to use the best detector that you have and to use that as your most reliable means of information. But it's also good to corroborate that with, for example, CR39 detectors or even X-ray film or other kind of detectors that you can think of. If you're looking at charged particles or neutrons, you might try to make to see if you can see activation due to gamma activation. Just try to see the same thing many different ways. It's better to see one thing 5 different ways than 5 things one way. Also, because we're in Vancouver and X-Files is very popular, I think we should take David Duchovny's motto very seriously: trust no one. Any one single instrument can be not telling the truth at a particular time. That's especially true for signals that occur without a real clear relation to something in the experiment. Like you do something, you wait 3 days, and then all of a sudden you get a signal. That's may not necessarily be incorrect, but I think we should be suspicious of that. Let's see, what I meant here was not background measurements, but control experiments. If you do no control experiments, that's bad. But also, I think even if you do just 1 or 2 control experiments, that's not enough. There needs to be several different kinds of control experiments. One particular problem is, for example, if you have a heavy water cell and then you do background with light water, you may get a different result because the gamma ray interaction or the cosmic ray interaction is different in heavy water than light water, so you'll get a different background. And okay, so that's what I meant for background. You have to make sure that when you do your background measurements, if you haven't changed the experiment unintentionally. I think the heavy water, light water case is a good example of that. Okay. It's also a very important feature to use shielding in order to increase the signal-to-noise ratio. But just a reminder that we have to be careful that we don't change the experimental geometry in doing that. Then from an electromagnetic point of view, I haven't said a lot about how to shield against electromagnetic radiation other than it's very important to use isolation transformers if they're available and try to shield everything, then shield it again. It may still be inadequate, but you have to do the best job that you can in providing shielding and making sure that your detector is in as good a Faraday cage as you can make. And that concludes the prepared remarks that I have, and both Professor Takahashi and I will stay later in order to answer either answer any questions you may have or debate them, depending on whether they answer or not. Thanks very much. And by the way, we won't be offended because it's been a long day, that if you'd like to leave at this point, you're more than welcome. Our feelings won't be terribly hurt.
May I ask a question?
Go for it.
One thing you didn't talk about was pulse shape discrimination.
Yes.
As a means of distinguishing noise from signal.
Yes. Well, one of the easy ways, I think, is with, you can often see with an oscilloscope when you have a lot of noise, because it typically doesn't have the same pulse width. Also, Dr. Takahashi, I'd like to defer to you because I know that you've made, in some of your papers, a very good example of how to discriminate. Okay.
that's the table of the data. Turning out the typical cross-section separation technique for neutrons, like scintillator. This scintillator, anything something viable or not, you can use this kind of technique. By using lifetime distribution for neutron, gamma ray, and noise distribution most fast this side. So usually we separate gamma ray noise and neutron by setting a discrimination level around here. This is a very long technique. However, if we make a very stable and long-run measurement, for this it's better to use two-dimensional analysis. Usual separation example, something like this. Since that we are running electrolysis, it's a gamma ray, it's a neutron. We set up a window, so-called region of interest for neutron. It's not here, because we have a gamma ray here, and the natural gamma ray background is 1,000 times larger than neutron background. So we need to set up a little bit higher side for separation. That is the SI technique in our experience. And the best way to use two-dimensional analysis this way is a right side, our side, gamma ray, neutron. By using this technique, we can watch all the time the gamma ray background, which has a Compton edge of calcium 40 around here. So we can watch the change of the amplifier gain or so with this also. And also take the gamma ray data simultaneously. So it's a good technique, however very complicated. And we can look at a similar technique for X-ray. This is a typical example of applied for cadmium telluride. It's a rise-time perovskite. The typical electromagnetic noise distributed around here. So by setting a region of interest around here, we can take out most noise. However, there are some distributed data around here. This is coming also real signal, but we may sometimes have a broader noise signal around here. It's better to cut this side and making a window this way. This kind of technique is used. Just an example.
Yes. Just a quick question for either one of you. Focus mostly on electrical or electronic equipment. I was wondering if you have any comment on X-ray films or things like that.
Yeah, I have some comment about that. There's I use this microphone. I think a very good paper for anybody interested in using X-ray films is one done by Raut and Srinivasan et al., which appeared in Fusion Technology about 2 years ago. And basically, there's about 10 or 15 ways that you can expose X-ray film in addition to X-rays. And one of the, if I can comment just a little bit about this paper, I don't see Dr. Srinivasan in the audience, but I thought it was a really strong paper, and it explained some very unusual observations that were obtained from deuterated and hydride palladium samples. And as I said, there are literally about 10 or 15 ways that you can expose film. And they went through each and every one of these, and they decided that that didn't explain the data. But so it's a very interesting fact that thus far has eluded explanation. But I guess what I would say, in general, X-ray film is not as sensitive as electronic detectors. It is not the preferred way to detect X-rays. If you do have a positive result, it could be due to a number of circumstances. But I think that it is valuable as a check for the detector readings that you may get if your experiment works. And also, there apparently is some kind of real effect that nobody understands that I think is worth pursuing. Dennis.
If you don't agree with X-ray films, what should we use for very low-level X-rays, assuming that we have nuclear paths that don't go through gammas and don't go through high energetic X-rays like helium-4 for just the relaxation of electrons, the electronic structure, not the nuclear structure, what would you propose to use?
I think I propose cadmium telluride as the preferred detector.
What about thermoluminescence materials? I'm thinking of some integrating material as opposed to, is there any of that that we can use?
Use whatever you've got. You know, as I say, I think that if you use 5 different detectors, that's not enough.
Yeah. Actually, detection of soft X-ray we have another problem. So if the signal is not reproducible, the best way to use just a detector or cadmium telluride detector set up simultaneously. And one covers some foil as molybdenum, which has this kind of K-shaped absorption edge. By using this absorption edge, we can identify signal. Well, this is really X-ray assumption. By this way, even the phenomena is one source, we can identify.
Yeah, I think that's not only use the detector, but use also this method that Professor Takahashi has described, where he measures the rise time and is able to distinguish between different types of counts, so that no matter what detector you use, somebody's going to say, well, I think that's not really a signal. And so you have to take every precaution you can to show that you have the real thing. And, you know, so that this kind of method is an essential, or can be an essential part of your program. It doesn't cost you extra money to do.
So we are combining
if you have a detector, right?
pulse shape and this kind of shape, switch in the cup and making a crossfire.
Yeah, maybe this was obvious and I didn't catch it. This is more directed to Dr. Takahashi. When you try to interpret a complicated spectrum, such as the one you have, where there are many kinds of particles at different energies and pilot pulses and perhaps other artifacts I don't know about, I would expect that the standard method of interpreting that would be a computer simulation, wherein you tell the computer the geometry you have, where your detectors are, what their pulse responses are, and so forth, and you do a Monte Carlo calculation, emitting the kinds of particles you think your preliminary analysis gave you, and then you adjust, or let the computer adjust the simulation until it gives the best fit. Is this what's normally done?
Yeah, we have done a very good simulation. So one example, computer simulation for power of just number 3. But however, we have to be careful about the condition of circuit setting up, because for making a computer simulation, we set up a parameter for the rising time and some changing time of time. Not setting by experiment by experimentalists and so on. And I think of course this kind of simulation can help somehow, but anyway, we need to check by experiment once. So we have done the experimental check for Palladium, for example. So the only by simulation calculation is not complicated enough.
Well, I would say that your curve 3 there, I would say was a simulation, is not a good fit. So do you go back and do a better simulation? Is that normal technique or not?
Yeah, even the one way, there are ways we repeat the experiment with different conditions, changing the detector stiffness and so on, changing angle and taking a consistency with the experiment. If we have a nice consistency, well, we can be.
I was wondering if very high-speed color black and white films could be useful in indicating the presence of low powerful data particles.
My opinion is that film by itself wouldn't be accepted as proof of radiation, but might contribute to understanding the phenomenon. But if you put film in front of something and you expose it, I think as a scientist you have to find out why that happens. So I think it's worth doing, but I wouldn't want to see that used as a primary basis for concluding that radiation exists.
the background from heavy versus light water. Have you ever actually seen any difference between heavy and light water and then your background runs?
Would you like to answer that one, Professor? I think I remember one of your papers pointing that out. But yeah, there is a difference in the,
Yes.
if you have heavy water,
Yes, we have a heavy, for example, neutron spectrum measurement. This is a typical example using neutron spectroscopy by LE230. This is somewhat axis is converted from real outside to record proton energy. But this is a typical cosmic ray background, cosmic ray with neutron background. And if we use heavy water for background run, I think we are measuring all the time this kind of spectrum. And if we see something different from this kind of exponential type distribution, maybe we are measuring some. Yeah, we have one example here. This is an example we took several years ago. This is not reproducible. I'm sorry to say that. This is the MCS counting. This is a background, right? We saw this kind of increase of neutron counts in MCS, and then we took the average Passell spectrum and took some difference between foreground and background, and we saw this kind of distribution, not exponential, but we have some structure. So we compared with some simulation calculation and to explain this. In that way, we can say some, but not very obvious.
yeah, but also I'll go further. If you have a beaker of heavy water in front of a neutron detector, you will always have more counts, more neutron counts due to that than if you have a beaker full of light water to the same level. There will always be a slight difference in neutrons.
So in our case of open cell, twin type experiment, so to say, we have two identical cells. One heavy water, and the Palladium cathode, nickel cathode, it's a brown one. And measuring the X-ray neutron spectrum, we believe with identical detectors and comparing at the time with two-dimensional analysis and so on. And if we see the difference, we can say some.
This is your chance between 10 o'clock and 10:30. And then we'll conclude the program at 10:30 and you can be on your way. Before we do that, somebody dropped a room key. If this happens to be yours, it'll be available in the back. And also, before I turn the microphone over to Professor Grazzani, I'd like to thank 3 women who have worked endlessly behind the scenes to ensure a smooth operation here this week. I was wondering if you would join me in a collective applause for Holly Coppridge with George Miley's office, Liz Streithall with Eneco, and Carol Storms with the Companion Program. And now I'll just turn it over to Tulio, and we'll go from there.
I thank Fred Yeager for giving to me and Mike McKubre the opportunity of giving the scientific summary. I understand that we did the same job last year, so it means that the last conference, so it means that it was appreciated, and so we try to divide the job, reviewing the scientific aspect the last time. I will briefly review the aspect concerning nuclear physics aspects. Now, I must say I'm quite astonishing in speaking in such a way. It's more typical to a party saying vote for me or something like that. The scientific, or please give cash for conclusion. It's not what I expect normally for a scientific review, in which the lack of view graphs is quite important. Anyhow, I will try to do my best. I can say that it was really enjoyed concerning the part that I will briefly review, because a lot of interesting, new, and comprehensive results were given. Of course, I cannot quote all the papers, so I have some sort of personal choice, and I think that everything it happens everywhere that you have to say something. Well, the first paper the paper that has most impressed me is that, I must say that I was both first, is that of Kazaki. And as a matter of fact, I think that this opinion was shared by all of the audience when they voted for where is Kazaki. When it was voted as the first of the 10 posters, the best vote. Well, is a continuation. I remind that Kazaki was doing this sort of work for the beginning. Is a typical nuclear physics experiment done in a well-reputed nuclear physics laboratory with method and technology well known and accepted by the nuclear physics community. And the results that he had shown this year was really very, very important and astonishing. He showed that going down to 2 keV with the energy of the neutrons of the small neutron machine that he has, he gets fusion rates on particular elements that Palladium oxide that were 50 times larger than in simple Palladium. So this is a dramatic demonstration of how the solid condensed matter effects are playing in the nuclear reaction rate. As a matter of fact, this, if very simply, if you fit the data by assuming an electron screening, which was found 600 electron volts, and as a matter of fact, extrapolating at zero, he found exactly or even better than the Fleischmann-Pond fusion rate. So it's an absolutely important result, and I think that certainly this line of experimentation will continue, and it could be that this sort of absolutely reproducible, well-done experiment could be the key to characterize the different alloys that are necessary after for the confusion experiment. On the same kind of experimentation was presented by the group of Professor Takahashi, again with a small neutron accelerator. And Takahashi was studying the different effects. I recall that from the beginning of confusion, Takahashi, working on the neutron spectrum, observed some anomalous high energy neutrons around groups of neutrons around 7 MeV. Instead, he found a normal 2 MeV, 2.5 MeV neutrons that are expected from the fusion reaction, but without also this sort of high energy neutrons. And he did the hypothesis, it is quite remarkable, with this very poor statistics data, and neutrons are very difficult to measure. They put forward the hypothesis that 3 neutron reaction could occur. As a result of this reaction, you could expect such a kind of high energy neutrons. He tried to repeat that with looking at the charged particles by similar chains of 3-body reaction, and again he succeeded. And under this repeating also some previous results that were obtained by Kazani. So that seems to me is two very important results. Now, going to the experiment performed with fusion cell, let me briefly review what it was observed. Well, we have practically 10 years of neutron measurement experiments, and certainly everybody knows that the neutrons, when observed, are very few in statistical significance, which is some sigma in the better of the best case. And so hardly a correlation between neutron and excess heat when found. Excess heat was observed. And as a matter of fact, a group of Okamoto presented here by Dr. Oya, if I'm not wrong, Dr. Oya, observed a remarkable, again, is a work of big patience, because he lasted several years to control all the parameters in order to find excess heat, which were not always found, of course, but quite a relevant number of cases. And more important, a correlation between, a quite nice correlation between neutrons emission, very low neutron emission, and heat was found. Was shown, fortunately I have no heat at Euros, was found a very nice straight line showing a correlation between neutrons and heat. Now, it was another product of the cold fusion cell, which is produced with more abundantly, but certainly not at the level expected from fusion reaction, is tritium. And in this particular aspect, we had a beautiful report by Plato that shows the results of a series of experiments performed at Los Alamos on 22 samples of different palladium alloys. And the tritium was measured in situ by very clever and colorful measurements. He was measuring at the same time the spectra and the half-life of the tritium in order to be sure that, that it was observed, it was really tritium. And in the case in which, in some cases, what he observed he was not using gas loading or, well, a particular type of gas loading. It was not an electrolytic cell, it was doing the plasma discharge in with neutron or hydrogen, and he found quite relevant amount of helium with a significance exceeding 10 sigma, so which is an experiment to show, again, without doubt, that there is production of nuclear ashes in this sort of experiments. The reproducibility was not so good, but this is a sort, apart from the first experiment, this is a sort of drawback that we still have in all these experiments. Now let me go to my favorite item, which is certainly the production of helium-4. Helium-4 is the last, in time, is the last nuclear ash that was found around, because there is considerable difficulty in setting up the experiment to measure by high-resolution mass spectroscopy this element. And we had, I could not repeat the measurement that was performed pioneering by mice and after repeated in several labs. I am mentioning here that are 3 experiments here presented, new experiments that have given positive results. 1 experiment that has given negative or doubtful results. In particular, Matsui, when he presented the results of the series of experiments that was performed on the new hydrogen energy project, he mentioned that he had some helium-4 analysis. In particular, she showed the results of the helium content from a wire of an experiment given by Cerani, in which heat excess was observed. And again, we had another further confirmation that when we have electrons that give excess heat, then we found helium. Another nice correlation was shown by Takahashi with working with closed cell. He found 4 cases in which he found excess heat. All the time he found helium exceeding by 1 order of magnitude the background. So that at ICCF-7 was just starting this sort of experimentation. So the present experiment that he presented was quite preliminary. Now the experiment is well showing what it was observed by several other experiments. I mentioned also that Dr. Lee, working on a deuterium palladium system in gas phase, after he takes 1 year, I remember well the sample in the Chinese patients, in the sample in the deuterium atmosphere, and he was measuring carefully the helium over neon ratio, which is one of the most important in order to be sure there is no external contamination from air, and he found that this ratio was about 2 higher, and demonstrating again that we had the production of helium when the experiment is performed in a proper way. Well, these are, on the other side, I must say that There is one experiment presented by Yamaguchi, that I will call Yamaguchi 2. It was a repetition done at IMRA of the experiment originally performed at NTT in Japan. Yamaguchi used a gas loading with a network structure and with some electrostimulation, and the experiment is completely performed in vacuum, and in order to avoid any possible contamination from Cristina Frigo. Now, he did the experiment and found something opposite was found in the first experiment. He found a reproducibility of excess heat of 100%. What he's saying, excess heat of the order of 8 watts with inputs of 0.1 watts. But he don't found, contrary to what was finding in the previous experiments, helium production. This is quite surprising. In the sense, not surprising because the helium did not exist, so you have to take believe first of all the experimental results. The point it is all the time you expect that when we are doing a Mark II experiment, we are doing better. As a matter of fact, the mass resolution of the Mark II experiment of Yamaguchi was a factor, more than a factor 2 worse than the first one. So, I speak along with Yamaguchi, and he admits that perhaps it is possible that the lack of resolution in this new experiments during IMRA would perhaps, he's not absolutely sure, explain this lack of helium-4. So probably there is the case of asking for a Mark III experiment of Yamaguchi in the hope that you found reproducible helium, or some other really hope that he found more excessive, no helium, nothing. But I think that there is a necessity that he's doing a third experiment. Well, the helium, because time is going running off. Helium is very much important not only for the DD reaction, but also concerning other mechanisms. For instance, Tom Passell is asking, is thinking of a reaction induced by boron, and again, helium will be a product. So it's very important that this line of results will be continued. Now, I will not keep time to my McKubre, let me say only the last few words. I was, up to this conference, I was absolutely skeptic about transmutation, I must say. Well, not only because it's extremely hard to give explanation, but also because the results so far presented, in my personal opinion, were quite poor concerning statistics on methodology and so on. I must say they are still skeptical, but not yet, not more absolutely. And in fact, the experiment that convinces me, since it was well done, that something is happening is that of Imamura, and which they observed, which is quite clever electrolytic device with all the control that I, of course, I know the time of describing. He found titanium production, which is quite non-explainable with contamination. And also, more important, we found an isotope shift between in iron 56 and 57, and that is seems to be quite bad in this sort of experiment. Now, also concerning the theory, I think that Peter Engelstein, after 10 years of work, has shown a quite interesting and comprehensive picture in which a possible explanation of all the phenomena is given, and in particular also for the concerning some transmutation. Again, one of the key elements is helium, and also Professor Kim working on accepted nuclear physics phenomena particularly concerning neutron halo nuclei, which are quite well accepted and recognized, give a hint of explanation of the cold fusion. And so I think that here I can stop my review. Simply with the final consideration, this conference has shown, in a certain sense, a turning point. Most of the results that I have presented were obtained by university group, university lab. Most concerned, most interested in the fundamental aspects than in the application. And so probably is a message for the continuation of this field. Probably is necessary more experimentation and speculation on the fundamental aspects and understand better how this nuclear physics, solid-state nuclear physics is working before trying to rush towards the construction of demonstration device. Thank you.
Rather than wandering around with a microphone like a rock star, as Tullio did, I'm perfectly happy to stand behind the podium and appear to be a politician. In fact, I'm not even too proud to ask for money for cold fusion. In fact, to demand money for cold fusion. I'm going to present less of a precise scientific assessment and more a judgment of what I've heard this week. I see the field becoming polarized somewhat. If you imagine a spectrum from fundamental research on one end to engineering development on the other, the history of cold fusion, as I've been associated with it, is mostly concentrated in the middle. People have been attempting to make small demonstration objects with the purpose of attracting the attention of large-scale engineering development. So heat experiments in the attempt to produce meaningful levels of excess heat have really dominated the history of this conference. Not so at this conference. I see a polarization between groups doing fundamental work, much of it materials related, and the break towards rapid engineering development characterized by ENICO, for example, SETI, Blacklight Power, who are not, I think, represented here. In some senses, this polarization is good. It's certainly good in that the two groups continue to attend the same conference so that they can cross-fertilize each other. Perhaps not a well-chosen phrase. With respect to the materials aspects, I know some very, very good science coming out of the cold fusion field. The Wednesday morning session that I was fortunate enough to co-chair with Franco Scaramuzzi started, I think, with Celani, ended with Domino. Perhaps the best sustained session at a cold fusion conference that I've attended. And I've been to every conference and have attended most of the sessions. I was very impressed at the sustained high level of reports, the logic, the reasoning, the structure of the experiments and their results. And it was once the time that we, in designing and organizing these conferences, put the least interesting papers into the materials section. The people who talked about materials were really those people who were trying to do excess heat experiments but hadn't succeeded in getting any results. So they talked about materials. I've even done it myself. Now, the strength of the field is in the materials sessions. People have recognized that this is where the problems lie and are turning their attentions and intellects to solving the problems. For me, this is a very, very strong step forwards. And in this particular context, I was very impressed, and have been for some time very impressed with the strength of the Italian contributions in this field, in this area. And it seems to me to be utterly appropriate that ICCF-8 will be hosted in Italy. With respect to the other polarity of this field, the engineering development, well, first thing is that it indicates that there is money, there is optimism, and I hope it also indicates that there is a demonstration object in clear sight, so this obviously is a good thing. In some senses, this polarization is bad, or unfortunate. It means that the materials issues have not been resolved, so we're forced to work on them. We've been working at this 9 years. It's taken a while to recognize, I think, or to gain a consensus that there is a significant materials-induced irreproducibility in this system. And for me, this is a personal affront because I've been saying it year after year after year. Finally, the world has probably come to a separate view that this is in fact the case, and a great deal of effort has been put into it, but the problems are profound. The problems of palladium, the problems of the electrochemical interface are truly, awesomely profound problems, and at the moment I don't see the resource directed to it to solve these problems in any realistically short time. So I come back to my first point, give money to cold fusion.